Well, I hope you're ready for some big-time math tonight. We're going to continue to investigate our volume by revolution topic, but we're going to get a lot more detailed and a little trickier tonight as we learn how to do the washer method. And this picture, I think, is worth 1,000 words. We're taking this goofy-looking region, this yellow-shaped bounded curve, and we're going to rotate it or revolve it around the x-axis. And as we do so, what's happening is, because the region is clearly above the axis of rotation, we're creating a big hole in the middle here. And you'll notice the washer we've drawn here. And just in case you were wondering what the word washer meant or the shape it was trying to describe, I want you to visualize this green donut-shaped oval. And that's what we're going to try to investigate tonight, how to find the volume of one of these washers and how to add them all up and so forth. So first things first, what in the world is the big difference between a washer and the discs that we saw last night? Well, the big difference here is, and you'll notice, and I'm going to draw my rectangular slice anywhere within the region. I could have drawn it over here if I wanted to. I could have drawn it up here if I wanted to. But I'm going to put mine, I tend to kind of centrally locate mine. You'll notice that the slice is not touching the axis of rotation here tonight. There's this big gap, all right? We got a big gap right here, and that's what tells us it's a washer. So to just kind of recap, last night when we were doing a disc, our rectangular slice was sitting or touching the axis of rotation. Okay? So there was no gap last night. No gap whatsoever. And I'll just say axis of rotation, AOR. Whereas tonight, when we're doing with our washer, we're going to have a giant gap. Well, I shouldn't say giant. There's going to be a gap of some sort. It might be tiny, it might be big, but there's going to be a gap between my rectangular slice and the axis of rotation. Let's see if we can spell slice. Okay. And the axis of rotation. So that, in a nutshell, is the difference between a disc and a washer. So our big goal now, and I'm going to try to challenge you as much as I can, and rather than just giving you the formula for washers, and it's an exciting formula, but I think it's a lot more exciting if we try to derive it ourselves. It'll have more meaning, we'll understand where it came from, and we'll have a better chance of remembering it correctly, months from now. So I want to derive a generic formula for washers, and as we've showed you, and maybe I can blow this picture up a touch. Let's see if that works. Okay, that didn't get too blurry. That's not too bad. We've got this rectangular slice, and we'll notice tonight it is not touching the axis of rotation. We've got this gap in between the slice and the axis. So what's happening is we've got capital R, which stands for my outer radius, and then I've got lowercase r, which represents my inner radius. And so capital R is the distance from the farthest edge of the slice to the axis of rotation, and little r is the distance from the closest edge of the rectangular slice to the axis of rotation. And then, of course, W is the width of the slice. Now, we want them to be really, really, really thin. But just, generically speaking, how would you find the area of a donut back in the day, or maybe a circular-shaped driveway or something? You would do pi r squared, and that would be the area of the big circle. So we're going to say capital R is the big radius. And then you would subtract out the area of the smaller tiny circle. So little r would be that little rascal. And the difference of those two circles would leave you with the space in between the two circles. And that's exactly how we're going to go about tonight. So if you want to find the volume of this particular washer right here, what we're going to do is we're going to go ahead and say, well, it's going to be the area of the bigger outer circle. So I'm going to go pi capital R squared minus the area of the little tiny inner circle. And then we're going to multiply it by its width. Now, as we've said before, we're going to say width is the change in x. And as that change in x gets infinitely small, we describe it with dx. Now, let's say you've got the volume of a bunch of separate washers. You've taken a certain region, you've chopped it into a bunch of infinitely thin slices. You found the volume of each individual slice. How do you add them all together? Well, that is the beautiful part of calculus, ladies and gentlemen. It is the integral that swoops in and saves the day. It is the integral from A to B that acts as our addition as we attempt to add all of the individual volumes of those skinny washers together. Now, a lot of times what you're going to see us do is you're going to see us factor the pi out, integrating from a to b, and it's capital R squared minus little r squared. Now I'm going to share a little insider tip with you. That is the volume formula that we're going to use, so we just derived it. One of the top mistakes on the exam is that students try to subtract the two radii first for some reason and square the difference. That is a huge no-no. We don't want to do that ever, 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 ever. And you'll hear me say it many times. We're going to square each individual radius one at a time and then subtract later. All right, so before we jump into our first live problem, I want to get ourselves organized, and I just want to go over some real important steps that I try to go through and rehearse each and every time. I think the first one goes without saying. We're going to come up with a great sketch, and I also just want us to really put a lot of energy into getting accurate intersection points. You know, whether we got to set the two functions equal to each other to find the intersections, or whether we're going to graph them on our calculator and do that, and and don't forget to store those intersections so that you don't lose any of your decimals. Whatever it takes, we want to get those intersection points. I want you to identify the axis of rotation. Again, a very little detail, but it's these little details that if you build good habits right now, starting now, then all these little details are going to pay off when you get to a quiz, you get to the test, you're going 100 miles an hour, and it's all these details that are going to save you and bail you out. All right, next thing I want you to do in number 3 is draw a very neat rectangular slice. In these pictures, there's going to be a lot going on. So take your time and try to be neat right from the get-go, right from the very first sketch you make. Your rectangular slice is going to be really neat. And then what I'm going to have you do is I'm going to have you draw some squiggly brackets. All right. Not exactly sure how to spell squiggly, so we're just going to make it up right now. Feel free to share your spelling with me tomorrow. We'll compare ours and see if we were even in the same ballpark. But I want you to draw a squiggly bracket that represents capital R, and then you're going to draw a little itty-bitty squiggly bracket to represent the little r. So each radius is going to have its own squiggly bracket. Then just ask yourself, am I working with a disc or a washer? How do you know? Well, it goes back to what we said on the first or second slide. If your slice is touching the axis of rotation, you've got a disc. If there's a gap between your slice and the axis of rotation, you've got a washer. It's that simple. Now, assuming it's a washer, and they're going to be washers tonight, I want you to identify your outer radius. And of course, that's after you drew your squiggly bracket. And also identify your inner radius. Okay, just list them off to the side. Here's my capital R, here's my little r. And that's something that I'm definitely going to consider when it comes time to award partial credit. And then number 6, we want to identify the correct bounds. Where did this region start? Where did it end? And then finish it off. We're going to write an integral expression to represent the volume, and be sure to square each individual radius. And that's what we talked about on that last slide. Make sure we don't subtract them first. We're going to square them first and then subtract them. Well, I'll tell you what, I think we've had a pretty good beginning, and I think at this point, rather than continuing to talk about it, we need to just dive in and get our feet wet and start with an example. And so what I want you to do is I want you to consider the region that's bounded by, we'll say f of x equals 8 radical x, and then we'll say g of x equals x squared. So just in an effort to save some time here, and we're going to revolve this first one around the x-axis. All right, keep it real simple for our first one. What I want to do is I'm going to cut to the chase here a little bit, and I'm going to say, of course, we know what x squared looks like, and I'm going to limit myself to the first quadrant. Of course, you could draw in the second, but it's going to be meaningless here for this one. And then 8 radical x grows pretty fast and gets up there. And I found the intersection point, and they intersect when x equals 4, and the y-coordinate happens to be 16 when they do that. And of course, I didn't mean to overlook the most obvious intersection, that would be at 0, 0. So we've got our region that's bounded between these two curves, and I want to take this football-shaped two-dimensional space and revolve it around the x-axis. So I'm going to identify my axis of rotation. I'm going to draw the best rectangular slice that I can. You notice that there is a gap between the slice and the axis of rotation right here, so we've identified it as a washer. Now I'm going to draw my first squiggly bracket, and that's going to identify my outer radius. And what I did is I just started at the tip top of the slice and I went down to the axis of rotation. And to find the length of that outer radius, I'm just going to do upper minus lower. You've probably never, ever heard me say that before, huh? So upper minus lower, and the upper function is, what's that going to be? 8 radical x. Luckily, the lower function is just y equals 0, so 8 radical x is the length of my outer radius. And then let's tackle the little guy on the inside, the little itty-bitty inner radius, little case r. And I'm going to do upper minus lower again. That's going to be x squared minus 0. And now we're ready to set up our integral and write our formula. Oh, real quickly, let me just clarify here in case it looks too messy. My outer radius is 8 radical x. My inner radius is x squared. So volume is going to be pi. Integral from, well, we started at x equals 0, and we finished at x equals 4. So, whoops, how about we try some numbers there, Mr. Hill? All right, there we go. We're rallying. We got our 0, we got our 4. We're going to take our outer radius, and we're going to wrap it up, and we're going to square it, minus the inner radius. Again, wrap it up and square it, and of course, bring your own dx and tack it on the end. All right, so where would you go from here? Well, it's not too bad, I'll tell you. It's not too bad. Don't worry about distributing that pi. Leave it out front. Leave it out front. So we got 64x minus x to the 4th. Not bad at all. And now I'm going to go ahead and I'm going to just find the antiderivative of each term. And that looks like it's going to be 32x squared minus 1/5 x to the 5th. So got my bounds of 0 to 4. Don't need to change my bounds. Never had to use a u sub, and that's pretty common on these problems. They're going to be pretty straightforward. And I tell you what, you plug in that 4, and let's see, so that's going to be 32 times 16, whatever that happens to be, minus 1/5 of x, 4 raised to the 5th power. And then you're going to subtract a bunch of zeros, and numerically, whatever that turns out to be is the volume of your new three-dimensional shape. And I tweeted this the other night. I said, you know, I love these volume problems, and I just wish that I could visualize them a little bit better as to the shapes they create. And I know some of us are a little better at it. Some of you guys are more artistic, and it makes more sense to you than it does to me, perhaps. So more power to you. And let's go try another one. What I'm going to do here for a bunch of these is I'm going to stick with the same functions just to simplify things so we could really focus on our setups and identifying our radii and stuff. So g of x is going to be x squared. This time what I want to do is I want to revolve it around the line y equals -2. So just 2 units below the x-axis. So here we go. Let's put our x-axis a little bit higher this time. And I've got my x squared, and I've got my 8 radical x, and we know that they intersect at 4, 16. And this time I'm going to revolve it around the line y equals -2. So you notice there's even a bigger gap now between my slices and my axis of rotation. Not to be outdone here. Let's see. We got our vertical slice. Got to be perpendicular to the axis of rotation. Let's see. The distance of my outer radius, and again, keep preaching to yourself, upper minus lower. It's going to be 8 radical x minus the lower function down here, which is -2. So I'm going to end up saying that my outer radius is 8 radical x plus 2 is the length of the outer radius. Now my inner radius, again, is going to be a little bit longer than it was last time. The little radius is going to be x squared minus the lower function, which is -2. So the little radius is going to be x squared plus 2. So I'm going to have to make sure I wrap them up and square them real nice and tight here. Whoops, let's see, move it. Alright, so here's my setup. Volume equals pi, integral from 0 to 4, just like last time. And the outer radius is 8 radical x plus 2. Wrap it up, square it, minus the inner radius, x squared plus 2. Wrap it up, square it. Alright, if you want to throw square brackets on that entire thing, be my guest. I think it makes it look a little more organized and detailed. But if we were going to go further, we'd have to FOIL here. We'd have to FOIL over here. And then maybe one of the trickiest things is just remembering, once you get done foiling here, we're going to have to distribute that negative sign through the foiling before we can combine like terms and then even think about doing any calculus where we actually integrate. But I'm very content with the setup for right now. Well, I warned you at the beginning of this, the video tonight that we are doing some hardcore serious math, and we're just going to continue to get more and more and more sophisticated here. So what I want to do here, same region, f of x equals 8 radical x, and g of x equals x squared. But this time I want to revolve it around the line y equals 20. In other words, if you're keeping score in your notebook there, this axis of rotation is going to be above the region. Whereas in the last two, the axes were below the region. I think it's more straightforward. Now we're putting the axis of rotation above our region, and really it's not much harder, but there's just something, we just have to think about it a little bit differently. So let's go x-axis there. We got our x squared cooking. We got our 8 radical x cooking. Now they intersected at 16, so my y equals 20 is clearly above that region, and it has to be. As far as the calculus we do this year, the axis of rotation will never go through the region. It's either going to be clearly below, clearly above, clearly to the right, or clearly to the left. It'll never go in between the region. Okay, so I'll put my little spinny symbol on there to show that we're revolving around the line y equals 20. I'm going to draw my vertical slice here. Again, we've got ourselves quite the gap between. We've got all this gap in there. That's when I declared that it was a washer and not a disc. Now, think about your outer radius. It's the edge of the rectangle that is farthest away from the axis of rotation. So I'm actually going to go all the way down here. And I'm going to say that my outer radius is upper minus lower. Okay, did you catch that? Upper was the 20. Lower was the x squared. That was a little bit tricky there. But just keep telling yourself upper minus lower, upper minus lower. Okay, how about this distance right here for the little radius? Upper is 20 minus the lower edge, which is 8 radical x. So those are my individual radii. Let's go ahead and we'll set up a volume formula. Let's say that the volume is going to be pi, still integrating from 0 to 4. We're still starting at x equals 0. We're still ending at x equals 4. My outer radius is going to be the quantity 20 minus x squared. Wrap it up tight, square it. Inner radius is 20 minus 8 radical x. Wrap it up and square it. Throw a little dx on the end, and you are good to go. Alright, for the first time tonight, I'm going to just change up the region a little bit. Let's go ahead and let's consider the region bounded by y equals 6 minus x squared. Y equals 3. And we're going to revolve it around the line y equals negative 1. Alright, so I think we know what y equals 6 minus x squared looks like. We're starting at 6 on the y-axis. We're opening downward. And I'll tell you what, I probably should give myself just a little bit more room so I can get that axis of rotation in there. So we've got y equals 3 is about right there. Y equals 3. So here's the region that we're working with, and we're going to revolve it around the line y equals negative 1 down here. And that's my axis of rotation. We're spinning it. I'm going to draw a nice vertical slice anywhere within the region that's perpendicular. I'm going to identify my outer radius, and the length of that outer radius is going to be upper, 6 minus x squared, minus the lower. So if I clean that whole thing up, I'm really getting 7 minus x squared is the length of that outer radius. The length of my inner radius, because we got to take out that gap, we got to subtract the gap, is going to be upper, which is 3, minus the lower function. So I got a 4. And at first I'm like, really, just 4? But it does make sense that no matter where I draw that slice, whether I put the slice here, 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 or here, the distance from this line, which would be the lower edge, to this line right here will always be 4 units long. Alright, now as far as the volume goes, alright, we got pi, we got the integral, we got our outer radius, wrap it up tight and square it. Minus the inner radius, wrap it up, square it. What's the one thing that I've totally neglected so far and that I cannot finish without? I've got to get these bounds, don't I? Alright, now the good news is this graph is symmetric with respect to the y-axis, so what I'm going to do is I'm going to integrate from 0 to something and then double my entire answer, and that's very legal and highly recommended. So I really need to put my energy into getting this intersection point right here. What I'm going to do is I'm going to set the two functions equal to each other, and if I said 6 minus x squared's got to equal 3, I'm really saying 3's got to equal x squared. X is equal to plus or minus radical 3. And this intersection is radical 3. So there's a great setup. We're ready to rock and roll. All right, here's a real wild and obnoxious one for you. I want you to think of the region created by the sine curve and also bounded by the cubic function x cubed minus 1 and also the vertical line x equals 0. And I want you to revolve that entire region over the line y equals 2 and see what you get for a volume. So we've created quite the interesting shape here. The sine curve from 0 to pi. We've got x cubed minus 1, which is going to cross the y-axis at -1, cross the x-axis at 1, and shoot upward. And then, of course, the line x equals 0 would be right here. So we're looking at this interesting region, very creative looking shape. And now we know the sine curve had a height of 1, so the line y equals 2 is going to be somewhere right around here. Y equals 2, spinning around that line. And let's go ahead and draw our vertical slice. And I'll tell you what, if you're feeling it, if you're really feeling it tonight, go ahead and hit that pause button and go set yours up and see if you come up with the same thing I've got. So my first thought was the outer radius is going to be that distance right there. And if I do upper minus lower, I've got to make sure I use parentheses around that function. And I'm going to end up with 3 minus x cubed for that length by the time you distribute the negative. Now my inner radius is going to be this little rascal, and that's going to be, again, upper minus lower, so 2 minus the sine curve. Now I just got to set up my integral now. So I've got volume equals pi, integral from something to something. Got my outer radius, wrap it up, and square it, minus my inner radius. And we've talked a little bit about this in class the last few days. And I know it sounds weird, but I think all great mathematicians, I think they do a lot of self-talk. And I can't emphasize that enough. A lot of self-talk. Walk yourself through it. Again, I think when you establish those good habits and you establish consistent repetition, it's going to eliminate careless mistakes when the heat is on and you're in the pressure moments. Now, I think definitely the shading region started at 0, so there's my lower bound. Now, I do need to go get that intersection point. I'm going to cheat just a little bit right now, and I'm going to call it alpha A. So that is entirely on the calculator. I'm not going to set these functions equal to each other and solve it algebraically. I'm going to find that intersection point using the calculator, and I'm just going to make sure I store it. I'm going to go back to my home screen, store that intersection in alpha A, and get ready to rock and roll, and then plug the whole thing into my calculator. Now, if I'm correct, I think we've done 5 live examples so far, and they all had something in common. Every single one that we've done so far used a vertical slice, okay? And because we were using vertical slices on all of them, vertical rectangular slices that were perpendicular to our axes of rotation, what that means is everything we did tonight was in terms of x so far. And that leads us into our next discussion. And what do you notice that's interesting about this particular picture here? We had some kind of rectangular slice, and this one's being revolved around the y-axis. Okay? So if you've got slices that are perpendicular to the y-axis and being revolved around that y-axis, now everything needs to be in terms of y. So that's our new theme here, is we're going to start to work with horizontal slices, which implies instantly, and this is non-negotiable, instantly everything has to be in terms of y now. And that includes not only the functions themselves, but it also includes the bounds, and that's one of the sneakier things. We've got to make sure that the bounds are in terms of y. So let's go back and pick up with the same region we were working with earlier. Let's consider the function y equals 8 radical x. I think we were calling it f of x earlier. And then we'll also work with y equals x squared. And this time I want to revolve it around the y-axis. So red alert, you've got an axis of rotation that's vertical. Therefore, your slices are going to be horizontal, and everything is going to be in terms of y. All right? So did you catch that train of thought? My axis of rotation was vertical, and that meant that my slices had to be perpendicular to that, so they're horizontal. And as soon as we mentioned that the slices were horizontal, that meant that all of our functions and bounds had to be in terms of y. So that was kind of the train of thought that went through my mind. All right, so we've got the y equals x squared, we've got 8 radical x, and now we're trying to revolve it around the y-axis. So let's go ahead. I've got a horizontal slice here. Again, disc or washer, how do you decide? How confident are you? Do you see the gap right in here? So because of this gap, we're definitely going to say that it's a washer. And my outer radius is this length right there. Now, we're not doing upper minus lower anymore, are we? We're going to ask ourselves right minus left. Now, bear trap number one. What is this equation right here? We can't say y equals x squared anymore. We've got to take this bear, we've got to solve for x. And the new name of this function is going to be radical y. Alright? So I'm going to say radical y minus 0. And that is the length of my outer radius. And then the inner radius gets even more interesting. This distance right there. Again, I got to take this function, I got to divide the 8 over, and then I've got to square both sides. So I'm thinking y squared, and this is going to get messy, y squared divided by 64 is the length of my inner radius. So let's go ahead and build this one, and we'll set it up. And I think the bounds are going to have a nice little surprise for us too. So let's go volume integral from something to something. We got our outer radius, wrap it up and square it, minus our inner radius. Again, wrap them up, square them, tack your own little dy on the end. You certainly don't want to lose a point because of that rascal, of all things. Now, where does your shaded region start? Okay, this region starts as low as y equals 0. Okay, how high does it go though? What's that y coordinate at its tip top there? I'm going to say the y coordinate up there was a 16 because I think earlier we said it intersected at x equals 4 but y equals 16 up here. So that needs to be your upper bound on your integral. From there you could square each term, you could combine any like terms, which there wouldn't be, and you'd be ready to integrate from there. Alright, one more big problem for tonight. I know it's a long video, but this is a big time topic and we're getting after it tonight. And so we're thinking, let's just stick with the one we've got, y equals radical 8 radical x, y equals x squared. This time I want to revolve it around the line x equals 6. So let's see what that looks like. Again, my axis of rotation is vertical, therefore my slices are horizontal, therefore everything, including both the function and the bounds, will be in terms of y. So let's say there's my y equals x squared, there's 8 radical x, and here's my axis of rotation over here at 6, because remember the intersection was at 4, so my axis of rotation is clearly off to the right. Alright, we got a slice with a big gap between the slice and the axis of rotation, just as you've expected all night tonight. The outer radius, how long is the outer radius? Alright, right minus left. Right edge, which is 6, minus the left edge, which is y squared over 64. So let's say 6 minus y squared over 64. That is the length of the outer radius. I think we're getting good at these radii, hopefully. Hopefully we feel decent. Just keep saying right minus left, right minus left. Now we've got our inner radius. Hopefully the color helps as well. That's something we didn't have in the past. Let's see. So we've got 6 minus, what would that be? That was radical y, right? So I just went from right edge to the left edge. 6 minus radical y, and now we are ready to rock and roll. We can set up our integral. So let's say volume is pi, and we're going to integrate as low as y equals 0 and as high as y equals 16. The outer radius, let's see, 6 minus y squared over 64. Wrap it up and square it, minus the quantity 6 minus radical y. Wrap it up, square it, tack on your dy. Ladies and gentlemen, let's put a big old exclamation point on there, and that is not a factorial. That is a celebratory act. It's saying you survived your first washer video, and I think you did quite well. Hopefully we'll be able to sort it out tomorrow, and we'll really take that next big step. All right, we'll see you.